All right, welcome. Today we are going to do something pretty incredible. We're going to crack open one of the most famous laws in all of science, Newton's second law, and ask a wild question. What if a key to modern physics was hiding there, in plain sight, for over 300 years? Let's get right into it.
Okay, so full disclosure right up front. Everything we're about to walk through comes directly from the really fascinating analysis in Chapter 2 of the book Newton and Relativity. We're basically unpacking their argument step by step because it presents a truly remarkable idea.
And that idea kicks off with this really provocative question. What if F equals ma, the equation we all memorized, isn't the whole story? What if Newton's original law actually held a secret, a hidden potential that points straight towards relativity?
To get to the bottom of that, we have to go back to what Newton actually wrote. I'm not talking about the simplified version from our high school physics class, but the full original law for what he called the variation of momentum.
So here we go. Newton originally said that force is the rate of change of momentum, which is dmv/dt. Now this is where it gets really interesting. When you just apply the product rule from calculus, basic math, this equation naturally splits into two pieces. The first part, mdv/dt, is the one we all know and love. That's force causing a change in velocity, acceleration. But look at that second term, Vm dm/dt. This part says that a force can also cause a change in an object's mass.
And this really shows you just how incredibly ahead of its time this was. I mean, think about it. Newton baked a term into his law for something, variable mass, that no one would be able to actually observe or prove for centuries. The possibility was right there in the math from day one.
Which, of course, leads to the big question, right? If this super powerful second term was there all along, why did it get dropped? How did F equals ma become the law that ran physics for the next 2 centuries?
Well, the answer really comes down to the world Newton was living in. The fastest speed he could have possibly observed was something like the Earth's orbit, which is about 30 kilometers a second. Now that sounds crazy fast to us, but it's just a tiny, tiny fraction of the speed of light. And at those slow speeds, any change in mass is so small you could never ever detect it. So it made perfect sense for him and everyone who came after to just focus on that first term. And just like that, classical mechanics was born.
And you have to remember, his entire framework was built on ideas of his era, mainly the belief in an absolute unchanging time and an absolute immovable space. We know now that's not how the universe works, but those ideas essentially boxed his mechanics into a special borderline case, not the complete picture.
So for hundreds of years, that second term just sat there, unused. But what happens when we can finally put it to the test? Let's jump forward to today, to the era of particle accelerators. These incredible machines that can push particles to the absolute edge and test Newton's full equation.
So to do that, the authors of the book first switch lenses. They translate the force equation into an energy equation. Think of it this way. When you pump energy, dE, into a system, it has to go somewhere. It can go into the first bucket, mv/dv, and make the object go faster, or it can go into the second bucket, v²dm, and increase the object's inertia, its mass. It's the same two terms, just a different way of looking at them.
And would you look at that? Here's what the experiments actually find. This table shows it all. At low speeds, the kind Newton dealt with, pretty much 100% of the energy you put in goes to changing the speed. The mass change term is effectively zero. But as you get closer and closer to the speed of light, the exact opposite happens. The particles barely speed up at all. Instead, almost all of that energy gets funneled into increasing their mass.
And that leads to this really crucial result. In that very specific limiting case where the velocity is approaching c, the energy equation basically simplifies down to dE equals c²dm. Now the authors are super careful to point this out, and it's important. This is not a general proof of mass-energy equivalence E equals mc². Instead, it's a fascinating result that just naturally emerges from Newton's original law when you push it to its high-speed limit.
The fallout from this is huge. It means mass isn't some fixed constant thing. It means there's a cosmic speed limit, because eventually energy just makes you heavier, not faster. And it means the simple math we use to add speeds together just breaks. To really describe how things move at any speed, you need both pieces of Newton's law.
So, if the experimental evidence for both terms is so solid, why isn't this how we all learn physics? Well, this gets us to a big disagreement in how mainstream science has decided to handle this exact problem.
You basically have two major camps. The first, which you'll see on places like Wikipedia, basically says Newton's law is just wrong for variable mass. End of story. The second camp, championed by giants like Richard Feynman, says, okay, the law was made for constant mass, but we can fix it by bolting on an external correction, specifically Einstein's relativistic mass formula.
But the book's core argument is that both of these approaches kind of miss the point. Physicists inherited this beautiful, complete two-term law, but for historical reasons, they only used one term. And when that one term started to fail at high speeds, instead of going back to the original law they already had, they chose to patch it with these external relativistic interventions.
And that brings us to the book's elegant solution, an intuitive third path that says, hey, what if we just use the full power of the equation Newton gave us in the first place?
This picture shows it perfectly. Physics has a great handle on the classical domain over here, where only speed changes, and it totally gets the limit domain over there, where only mass changes. The book argues that we need to focus on this missing middle, the zone where both things are happening at once. That, they say, is the domain of true, complete Newtonian mechanics.
And here it is. This is the payoff. By just staying inside Newton's original framework and using both terms, the authors show how you can derive the famous relativistic mass formula directly. No external patches needed. That's path B, the intuitive route. It suggests you don't actually need complex fixes like Lorentz transformations because the answer was already there, waiting inside Newton's second law.
So really the key takeaway is all about language. The authors make a very clear distinction. Classical mechanics is the version that only uses that first term, but Newtonian mechanics is the more powerful system that uses both terms. When you look at it that way, Newton's work isn't just a historical footnote. It's a complete mathematical engine that's powerful enough to derive relativistic ideas all on its own.
And that just leaves us with this one last incredible thought. If a huge piece of relativity was just sitting there, dormant, inside Newton's law for centuries, just waiting for us to get the right data and ask the right questions, what else could be hiding in plain sight? What other breakthroughs are just waiting for us in the original words of science's greatest thinkers?